First, I would like to thank the organizers for giving me an opportunity to give a talk in this special session. To start with, this is a joint work with Acharya, Kirova, and Shivaji. I want to give a motivation first. In 2018, we studied this particular elliptic boundary value problem where the parameter lambda influences the equation as well as the boundary condition. On the boundary, this function mu is a non-negative increasing function, and here are the shapes of mu. Here are some shapes of mu that you would expect. Okay, and here are the three cases that we studied. We studied the case when f of 0 is equal to 0, f of u is your reaction term, by the way, f of 0, 0, f of 0 positive, and f of 0 negative. Those are the three cases we studied. And for each case, we assume that we either have a unique fall in 0 R naught or the limit of the function is positive. Okay, limit of the function is positive means you don't have a fall in 0. And now I want to show you some results that we established for this model. I want to show you the results that we established for this model for this particular case. F of 0 is equal to 0 and f prime of 0 is equal to 1. Under certain assumptions, we proved that this model has at least 3 positive solutions for a certain range of lambda for lambda bigger than a1 mu. Okay, by the way, this bifurcation diagram is plot for subnorm of u versus lambda. Okay, we showed that we have at least 3 positive solutions for a certain range of lambda and the positive solution u lambda such that the subnorm of that solution goes to r naught as lambda goes to infinity. Okay, and here is the bifurcation diagram for the case when r naught is infinite. That means there is no fall in 0. Again, we showed that we have at least 3 positive solutions for a certain range of lambda and the positive solution u lambda such that the subnorm of the solution goes to infinity as lambda goes to infinity. And by the way, here this a1 mu is the principal eigenvalue of this eigenvalue problem, which is the associated linearized problem to our model. Okay, and the existence of the principal eigenvalue of this eigenvalue problem is not entirely trivial. The proof of the existence can be found in this paper, in our paper. The details are given here. All right, here are some other studies where you can find these types of studies where the parameter influences the equation as well as the boundary conditions. All right, next I want to introduce my model of interest. Here is the model of interest. I take the previous model with mu lambda is equal to square root of lambda, and this time my reaction term f of s is ms plus g of s, where m is a positive constant, and this g of s is a function satisfying these properties. This is my hypothesis H1. I assume that g is an increasing function. G of 0 is 0, g prime of 0 is equal to 1, g double prime of 0 is positive, and g is a sublinear function. What that means is that limit as s goes to infinity, g of s over s is a 0. Okay, so that's my first hypothesis. Notice that when g of s is a sublinear function, this f of s is linear at infinity because this m is assumed to be a positive constant. And also I want to let you know that we studied even the case when m is equal to 0, but for today's talk, let me focus only on the case m is greater than 0. Okay, our reaction term exhibits a linear growth at infinity. All right, before I go into the next hypothesis, I'm going to take ak to be the principal eigenvalue of this eigenvalue problem. This a is the eigenvalue parameter and k is sitting here, it's a fixed number. And one interesting property that we can prove about this principal eigenvalue ak is decreasing in k. Okay, we can show that property. And also the existence of the principal eigenvalue of this problem can be found in this particular paper by Goddard, Morris, Robinson, and Shivaji. You can also see this decreasing property there. All right, next I'm going to take W to be the unique positive solution to this particular boundary value problem, in this problem, this A1 is the principal eigenvalue of this problem when k is replaced by 1. That's A1. Okay. And then I'm going to take V to be the solution to this particular boundary value problem, the unique solution to this boundary value problem. Having said that, here is my hypothesis 2 that I'm going to assume. My hypothesis 2 is I assume that there exists B1 greater than A1 greater than 0 such that the minimum of these two numbers is bigger than the maximum of these three numbers. In this hypothesis, this R is the radius of the largest inscribed ball inside your domain that you are working on. And this Cn, the constant Cn, is defined by this equation. Cn is the infimum of this expression with respect to epsilon. And here this n is the dimension of your domain. And here is my next hypothesis, H3. I will label that as H3. I assume that there exists B2 greater than A2 greater than 0 such that this quantity is bigger than Am plus 1. That is bigger than the maximum of these two numbers. Okay, notice that in this hypothesis, this Am and Am plus 1 are understood via this eigenvalue problem. Okay, Ak is the principal eigenvalue of this eigenvalue problem. All right. Here is the shape of a function which satisfies H1, H2, and H3. Okay, as you can see, you have this alternating convexity and concavity. Okay, when you have this alternating convexity and concavity, here is the shape of the function S over f of s. It's kind of a wavy shape like this. This wavy shape of S over f of s is what produces the multiplicity for us. Okay, in fact, if this function S over f of s is an increasing function, we can show that the solution is unique. Okay, so the bottom line is this wavy shape produces the multiplicity for us. All right, next I want to state my theorems, existence and multiplicity results. Here is my theorem 1. If we assume that H1 holds, then our model 1 is the model that I stated over here. Okay, so my f of s is ms plus g of s, and I take my mu lambda to be square root of lambda on the boundary. If you assume that H1 hold, then our model 1 has a positive solution u lambda for lambda between Am plus 1 and Am, and at least two positive solutions for lambda between lambda bar and Am plus 1 for some lambda bar less than Am plus 1. Also a positive solution u lambda for lambda less than Am and lambda close to Am such that the subnorm of that solution goes to infinity as lambda goes to Am from the negative side. And further, if we assume that H2 also holds, then our model has at least three positive solutions for lambda between these two numbers. Okay. From hypothesis H2, it is clear that this number is bigger than this number. Okay. All right, here is an expected bifurcation diagram which is drawn for subnorm of u versus lambda. You have at least two positive solutions for a certain range of lambda to the left of Am plus 1, and at least one positive solution for lambda bigger than Am plus 1, and a positive solution whose subnorm goes to infinity as lambda goes to Am from the positive side, and of course three positive solutions for a certain range of lambda to the right of Am plus 1. And recall that again, I take Ak to be the principal eigenvalue of this problem, and Ak is decreasing in k. And here is my theorem 2, and this is what produces the sigma shape bifurcation diagram for us. Okay, if we assume that H1 and H2 hold, then there exists some lambda star in this particular interval such that one has a positive solution u lambda for lambda between lambda star and Am, a positive solution u lambda for lambda less than Am and lambda close to Am, such that the subnorm of that solution goes to infinity as lambda goes to Am from the negative side, and at least four positive solutions for lambda between lambda star and Am plus 1. Notice that this interval is possible by our hypothesis H3. Okay, And here is an expected bifurcation diagram. You have at least 4 positive solutions for a certain range of lambda to the left of am plus 1. As you can see, in this region, you have at least 4 positive solutions. Okay, these 4 positive solutions produces the sigma shape for us. As you can see, you have this sigma shape, and of course we can show that we have at least one solution for lambda bigger than lambda star and lambda less than am, and the positive solution whose subnorm goes to infinity as lambda goes to am from the negative side. Okay. So this is the theorem that I am going behind for today's talk, and this is what produces the sigma shape bifurcation diagram for us. All right, next I want to give you an outline of the proof of theorem 2. For that, I want to introduce the method that we use to establish these results. We used the method of sub and super solutions. Let me talk a little bit about method of sub and super solutions. Here are the definitions of sub and super solutions. Any function psi satisfying these two inequalities is called a subsolution of our model, and any function z satisfying these two inequalities is called a super solution of our model. And here is an important lemma that we use to establish our results. If you have a subsolution psi and a super solution c such that your super solution is bigger than or equal to your subsolution, then there has to be a solution in between them, in between your sub and super solutions. And here is another lemma that we used to establish our results. If you have a small subsolution psi1 and a big super solution z1, and in between them you have another strict subsolution and a strict super solution z2, such that the strict subsolution is bigger than the strict super solution in at least at one point in the domain, then the conclusion is that there exists a solution u1 in this ordered interval and a solution u2 in this particular ordered interval, and there's a third solution u3 in this particular interval, in this particular space. This third existence of this third solution can be proved using degree theory, and of course the existence of these two solutions come as a consequence of the previous lemma. All right, now let me give you an outline of the proof of theorem 2. Recall that here is our theorem 2 again. This is the model that we are interested in. We have at least 4 positive solutions for a certain range of lambda to the left of am plus 1, and at least one positive solution for lambda between lambda star and am plus 1, and we have this asymptotic behavior. Okay. Due to the time constraints, I'm not going to show all those properties, but I want to show the existence of at least 4 positive solutions for a certain range of lambda to the left of am plus 1 for a certain range of lambda. Okay. So I'm going to show you the existence of at least 4 positive solutions. Actually, that's what produces the sigma shape for us. All right. To start with, what I'm going to do is I'm going to construct a sequence of sub and super solutions. First, notice that if I take psi1 is equal, psi naught is equal to 0, that's going to be a sub solution for our problem, because psi naught is equal to 0 is a solution to our problem. Remember, we are assuming that f of 0 is equal to 0 here. So it's going to be a sub solution for our problem because it's a solution. And then next, I'm going to construct a big super solution C1. Okay. And then in between them, I'm going to construct a strict subsolution psi1 and a strict super solution C2, such that the subnorm of this strict super solution is smaller than the subnorm of the strict subsolution psi1. Okay. If I have this setup from the lemma 2 that I stated earlier, we can see that we should have a solution which comes below this strict subsolution. Okay. From the previous lemma, we have to have a solution in this particular space. So that means there has to be a solution which comes below this strict subsolution psi2. Okay. So the bottom line is we are going to have a solution which comes below this strict subsolution if we have this setup. Okay. I'm going to prove these sub and super solutions now. Now let's construct this big super solution. Okay. I'm going to construct that super solution for lambda less than am plus 1. To construct that super solution, I'm going to take sigma lambda comma k to be the principal eigenvalue of this eigenvalue problem for a fixed lambda. Okay, and here are some interesting results that we can prove about the principal eigenvalue sigma lambda k. We can show that sigma lambda k is positive when lambda is less than ak, and sigma lambda k approaches to 0 as lambda approaches to ak. Okay, the proofs of these properties can be found in this particular paper by Goddard, Morris, Robinson, and Shivaji. This is the same paper that I showed you earlier when I talked about the eigenvalue problem, principal eigenvalue AK. All right, to show that, to construct the super solution C1, I'm going to take C1 to be m times theta lambda m. M is a constant that I'll be choosing later. Theta lambda m is the eigenfunction associated to this module. Okay, I'm going to show that this C1 is a super solution for lambda less than am. Then it will be a super solution for lambda less than am plus 1 because ak is decreasing in k. Okay, so am is bigger than am plus 1. All right, to show that this is a super solution, I'm going to consider this difference, negative Laplacian C1 minus lambda f of C1. What I'm going to do is I'm going to compute negative Laplacian Z1 using this eigenvalue problem because my C1 is m times theta lambda m. If I compute negative Laplacian Z1 and if I plug in C1 in my function f, my function f is, remember, it is ms plus g of s. Plug in the value of Z1, and if I factor out this m times lowercase m times theta lambda m, here is what you get within the parentheses. Okay, as you can see now here, if you choose your constant m large, this part will be small because we know that g is a sublinear function. That means if your m is very large, this part will be close to 0. But we also know that my sigma lambda comma m is positive if lambda is less than am. Okay, we assume that lambda is less than am plus 1. That means lambda is less than am because am is bigger than am plus 1. So this part has to be positive if you choose your m big enough. Okay, so that means we have this inequality. This difference is greater than 0 for m big enough. Now if you look at the boundary expression, because of these boundary conditions, we can see that this boundary expression is going to be equal to 0. Okay, that means C1 is a super solution for our model if you choose your m large enough. Okay, so we have this big super solution. Next, I'm going to construct a subsolution. This subsolution psi1. For that, I'm going to take sigma lambda comma m plus 1 to be the principal eigenvalue of this eigenvalue problem. And I'm going to take, by the way, I'm going to construct this subsolution for lambda less than am plus 1 and lambda close to am plus 1. Okay, I'm going to take psi1 to be delta lambda times theta lambda m plus 1, where theta lambda m plus 1 is the eigenfunction associated to this eigenvalue problem, and delta lambda is defined this way. Okay, in this expression, this a star is a positive constant such that f double prime of s is bigger than a star for small s. Okay, and notice that here this delta lambda goes to 0 as lambda goes to am plus 1 because we know that sigma lambda comma m plus 1 goes to 0 as lambda goes to am plus 1. So that means if I choose my lambda close to am plus 1, this delta lambda is small. That means my psi1 is small if I choose my lambda close to am plus 1. All right, having said that, I'm going to consider this difference, negative Laplacian psi1 minus lambda f of psi1. We can compute negative Laplacian psi1 using this eigenvalue problem. It is going to equal to this expression. And I'm going to replace this f of psi1 using the Taylor series expansion and using the fact that f of 0 is 0, f prime of 0 is equal to m plus 1. Okay, if I replace that, you are going to get this. With this eta is a number between 0 and psi1, and I can assume that this number eta is very small if I assume that my lambda is very close to am plus 1, because when lambda is very close to am plus 1, my psi1 is very close to 0. All right, now if I pull out the psi1 from this expression and replace this f double prime of eta by a star, you get a bigger quantity in the right hand side. At the same time, I'm going to replace one of the psi1s here by the minimum of psi1. Okay, then again you get a bigger quantity in the right hand side. Now by the choice of delta lambda, this part is going to be 0. Okay, so that means we have this difference is strictly less than 0. And now if you look at the boundary expression, d psi1 over d eta plus square root of lambda psi1, that is going to be equal to 0. This is clear because of these boundary conditions. Okay, this eigenvalue problem, this theta satisfies, theta lambda m plus 1 satisfies the same type of a linear boundary condition as in our problem. All right, this implies that psi1 is a strict subsolution for lambda less than am plus 1 and lambda close to am plus 1. Okay, what does that tell you? That tells you that psi1 will be a strict subsolution for lambda between lambda star and am plus 1 for some lambda star in this interval. Okay, such a lambda star exists. All right, I have this subsolution now. Next, I'm going to construct a super solution C2. Okay, I'm going to construct my super solution for lambda less than am plus 1. For that, I'm going to take sigma lambda comma m plus 1 to be the principal eigenvalue of this eigenvalue problem. And I'm going to take C2 to be the epsilon times sigma theta lambda comma m plus 1. This epsilon is a positive number that I'll be choosing later. Okay. To show that it's a strict super solution, I'm going to define this function h of s this way. Then notice that h of 0 is 0 because f of 0 is equal to 0. And h prime of 0 is equal to this particular number, which is positive because I am assuming that my lambda is less than am plus 1. Okay. So that what that means is that this function has to be positive for s small, because the function is 0 at 0 and the derivative of that function is positive at 0. So the function has to be positive for s small. Now I'm going to compute this difference negative Laplacian C2 minus lambda f of C2. It's going to be this expression. Now as you can see from this property over here, this is positive for s small. So that means this has to be positive if your C2 is small. Okay, but we can make sure that C2 is small if you choose this epsilon small. That means we have this inequality. This difference is greater than 0 when epsilon is small. Now, if you look at the boundary expression, again it is going to be 0 because this theta lambda m plus 1 satisfies a similar linear boundary conditions here as in our problem. So that means C2 is equal to epsilon times theta lambda m plus 1 is a strict subsolution for lambda less than am plus 1 when epsilon is small. So we have that strict subsolution. So now that means we have a solution to our problem which comes below this subsolution psi1 by lemma 2. Okay. All right, we need to keep that solution in our hand. Next, what I'm going to do is I'm going to construct another super solution C4. I'm done with these sub and super solutions. I'm done with this. I'm going to construct another super solution C4, strict super solution C4 for lambda between these two numbers, lambda in this interval. Okay. For that, I'm going to take lambda to be the unique solution to this boundary value problem, and I'm going to take C4 to be this function. Okay. And notice that since lambda is in this interval, lambda is this quantity is bigger than lambda. Now, if you compute negative Laplacian C4 using this boundary value problem, it is going to equal to this one. But this is bigger than this one because of this inequality. Okay. Now, notice that A2 is the subnorm of C4. Now, I can replace this A2 by something smaller to get something smaller in the right hand side because f is an increasing function. All right. So that means we have this inequality negative Laplacian C4 greater than lambda f of C4. And on the boundary, if you compute this boundary expression using the fact that your lambda is bigger than A1 over 2, we can see that this is going to be greater than 0. Okay, so that means this C4 has to be a strict super solution for lambda between A1, lambda in this particular interval. Notice that this A1 is a number which is less than this one. Okay, so C4 is a strict super solution for lambda in this particular interval. All right, finally, the last one I want to construct is this subsolution. I want to construct another strict subsolution. Notice that the subnorm of the previous super solution, strict super solution, is A2. Okay, I'm going to construct this subsolution now. Here is what I'm going to do. I'm going to look at this particular boundary value problem. This is the same reaction term, but I have this Dirichlet boundary condition this time. Okay, this problem has been studied by Shivaji and Ramaswamy, and they showed that in their study, they showed that this particular problem has a strict subsolution psi bar for lambda bigger than this particular number. Okay, with this property, the subnorm of psi bar is bigger than B2, and we know that B2 is bigger than A2 by our assumption. Okay, what I'm going to do is I'm going to take that subsolution psi bar and feed it in my reaction term, and I'm going to take psi 4 to be the solution to this boundary value problem. And then using the maximum principle, we can show that psi bar is less than or equal to psi 4, and this psi 4 is a strict subsolution to our model. Okay, so we have this as a strict subsolution, and notice that the subnorm of this subsolution is bigger than the subnorm of this strict super solution because B2 is bigger than A2. So what does that tell you? That tells you that since you have this subsolution psi 1, I can make sure that this psi 1 is small by choosing my lambda close to m plus 1. Okay, so we have a subsolution, a small subsolution, and a big super solution. In between them, you have a strict subsolution and a strict super solution. Okay, so that the subnorm of the strict super solution is smaller than the subnorm of the strict subsolution in at least at one point in the domain. Okay, so what that tells you is that by lemma 2, there has to be at least 3 positive solutions between these two sub and super solutions. Okay, remember previously I told you that there has to be another solution which comes below this strict subsolution psi 1. Okay, those 3 solutions together with that solution which comes below psi 1 gives you 4 positive solutions. Okay, and that gives you the 4 positive solutions to the left of am plus 1 for a certain range of lambda. All right, here are some references that I used in my talk. Thank you very much for your attention.